Good morning students. Welcome to our next lecture of data structures and algorithms. Our today's topic is AVL tree. Till now we have discussed about the binary tree, binary search trees and their techniques of inserting nodes in those types of trees. So today we will study about AVL tree. What is an AVL tree? AVL tree, first of all let's discuss about the main full form, main definition of AVL tree. In 1962, Russian mathematicians, there were three Russian mathematicians, G.M. Adelson, first one was G.M. Adelson, second one was Velsky, from there we got this V, G.M. Adelson, from there we got A, and E.M. Landis. L we got from the name Landis. So these three mathematicians gave this technique of AVL tree. That's why this is known as AVL tree with their names as short form. So AVL tree was given by these three Russian mathematicians in 1962. Now we will discuss about the technique that AVL tree follows. AVL tree uses the technique to balance the height of a binary tree. We have discussed binary tree in our previous lectures. A binary tree is a tree in which each node of that binary tree contains at most two subtrees. At most two subtrees means the node can have either one subtree or two subtree or not at all, or a zero subtree. That's why we are saying that at most two subtrees. So AVL tree is mainly used to balance the height of a binary tree. Height of a binary tree is the levels at which different nodes are inserted in a tree. In binary tree we were inserting different nodes at different levels, but we were not focusing on the height or balanced height of that tree. So in order to balance the height of binary tree, we have a technique known as AVL tree. So we will study about AVL tree and the technique how we can balance the height of a binary tree. We will study with an example, that is how we can balance the height of a binary tree. So in AVL tree, with the help of AVL trees, searching, insertions and deletions of the nodes, searching insertions and deletions in a tree which contains n number of nodes, those searching, insertion and deletion operations can be achieved in the time of order On. The time of order On. This will give the time in which we can search, insert and delete the nodes given in a binary tree which contains n number of nodes, and the time that it will take to accomplish these operations will be On, even in worst case. Even in worst case means maximum time that can be taken to accomplish all these operations will always be On. Maximum and minimum, both time is given by using On. So this was the basic introduction about AVL tree. Now we will see how we can balance the height of a binary tree using the technique given by AVL tree. So this technique or this balancing of height of a binary tree can be understood with an example. Here I have taken an example in which we will construct an AVL tree with the following data. In our data we have the numbers which will be used to construct the nodes of the binary tree. So in data we have 25, 45, 50, 55, 60, 65 and 75. These are our data elements that will be inserted in our AVL tree, and these data elements will be inserted in the nodes that we will create for our tree. So let's start with the solution. 25, we have first element being 25. So at first step we will start with the first node, that is 25. We will insert 25 in our memory as first node. Now after 25, after inserting 25, we will move towards the next element, that is 45. Now we will insert 45. For inserting 45, what we will do, we will compare it with the previously inserted element. The previously inserted element was 25. So we will compare the next element that we are inserting, that is 45, with the previously inserted element 25. Since 45 is greater than 25, and this property we studied in binary tree, that the element greater than the root node will always be inserted on the right hand side of the root node. So we will insert 45 on the right side of 25, because 45 is greater than 25. Okay, since 45 is greater than 25, that's why we have inserted 45 on the right side of root node 25. After inserting 45, we will move towards the next element. Next element is 50. For inserting 50, we will again compare it with the previously inserted elements. Our previously inserted elements contain 25 and 45. So we will compare 50 with 25 and 45. Since 50 is greater than 25, so it will come on the right side of 25. Right side of 25 already contains 45 as the next element. So we will compare 50 with 45. After comparing 50 with 45, since 50 is greater than 45, so we will further insert 50 on the right side of our element 45. In this way, we will insert these three elements, that is 50 is greater than 45, that's why we have inserted 50 on the right hand side of the node 45. Now this will give us a tree in right direction. This tree is in right direction and the levels are 25 is at level 0, 45 is at level 1 and 50 is at level 2. Since we are studying the balancing of height of a binary tree, we will balance the height of this tree so that we can get a height balanced tree or an AVL tree. So to balance this tree containing these three nodes, what we will do, we will take a critical node. Now this critical node is a node that we will rotate in order to balance our tree. Critical node is the node that will be used to rotate so that we can get a height balanced tree. So here 45 is our critical node, and after taking 45, we will rotate 45 in left direction so that we get a height balanced tree. So we rotated 45 in left direction. After rotating 45, that is after balancing 45, what we get a tree. In that tree, after balancing, we get 45 as the root node and 25 comes on the left side of 45 and 50 comes on the right side of the 45. Now if we want to check the properties of binary tree, we can easily check. The property of binary tree states that the nodes which are smaller than the root node should always be placed on the left hand side of the binary tree. So here 25 is smaller than 45 and 25 is placed on the left hand side of the root node. So this property gets fulfilled, and that property also states that the element, the node greater than the root node will always be inserted on the right hand side, on the right side of the binary tree. So 50 is greater than 45, that's why 50 is inserted on the right hand side of binary tree. Now checking the levels, 45 is at level 0, 25 at level 1 and 50 also at level 1. So we can say that this tree is balanced. Balanced means no other node is at such level that either from left direction or from right direction. That means if we have another node after 25, then our tree would not be called as balanced, or if we have node on the right side of 50, then also we will not consider it a balanced tree. So after inserting 50, our next element is 55. So what we will do, we will insert 55. For inserting 55, we will again check the conditions that we will compare 55 with already inserted nodes or already present nodes with the already present nodes in our binary tree. So we will compare 55 firstly with the root node. So 55 is greater than 45, that means there is no need to compare it with the leftmost node, that is 25, because after comparing it with root node we came to know that it is greater than root node. So we will move directly towards the right hand side of our binary tree. So we will compare 55 with 50. Since 55 is greater than 50, that means 55 will be inserted on the right side of the node 50. That's why we have inserted 55 on the right side of node 50. Now after inserting 50, our next element comes is 60. For inserting 60, we will again do the same comparison, that is we will start comparing it from the root node. We will compare 60 with the root node. Root node is 45. Since 60 is greater than 45, that means we will insert 60 on the right side of the root node 45. Now going towards the right side of the root node 45, there is a next node available, that is 50. So we will compare 60 with the already available node 50. Since 50 is less than 60, so 60 will further move towards the right side of the node 50. Further moving the right side of the node 50, there already exists another node 55. So we will compare 60 with 55. So 60 is greater than 55. So we will insert 60 on the right side of the node 55. That's why we have inserted 60 on the right side of node 55, because 60 is greater than 55. Now the tree that we have now is not a balanced tree. Not a balanced tree means 45 is at level 0, 25 and 50 are at level 1, 55 at level 2 and 60 at level 3. So this is not a balanced tree, because the left subtree of this binary tree is ending at level 1 only, and the right subtree of this given tree is ending at level 3. So this will become unbalanced. So in order to balance this tree, what we will do, we will again do the balancing 50 and 45. For balancing this right hand side of this binary tree, we will take 45 and 50 as our critical nodes. We are taking, again I am telling you, we are taking critical nodes so that it will become easier for us to balance those nodes, keeping in mind. So here 45 and 50 will become our critical nodes. Now after balancing, what we will get, 45 will become our root node. 45 becomes our root node. 50 will come on the right side, and since 50 is less than 55, So 50 will come on the left side of the node 55 and 60 will come on the right side of the node 55, because 50 is less than 55. That's why we have shifted left shifted 50 so that we get a balanced node. So now here our node gets balanced. This is at level 0, 1, 1 and these two are at 2. Now further inserting these remaining nodes, we will get at the end a height balanced tree, and that height balanced tree will be known as the AVL tree. So after inserting 60, our next element to be inserted is 65. So for inserting 65, we will again follow the same condition or same operation, that while inserting any new node, we will start comparing it with the root node. If the element that is to be inserted in our root node is less than the root node, then we will insert it on the left hand side of the root node. That means if the next element that is to be inserted is on the left hand side of our root node, then we will insert it on the left side. And if the element is greater than the root node, then we will insert that element on the right side of that root node. So next element is 65. For inserting 65, we will compare it with the root node 45. Since 65 is greater than 45, so we will move towards the right side of 45. Right side already contains 55. We will compare 65 with 55. So 65 is greater than 55, we will further move towards the right side of the node 55. Right side already contains the next node, that is 60. So we will compare 65 with 60. Since 65 is greater than 60, then we will insert 65 on the right side of our node 60. In this way we will insert 65. Now after inserting 65, our tree again gets unbalanced. This is at level 0, 1, 2 and 3. Now 65 comes at 3 and this tree becomes unbalanced. So in order to balance this tree, what we will do, we will take 60 as our critical node and make a left shift to balance this tree. For balancing, we will make a left shift of nodes using the critical node 60. So we will left shift our critical node 60. After balancing, what we will get, 55 will become our root node. 55 will become our root node. 45, since 45 is less than 55, so 45 will come on the left side of root node 55, and 60 is greater than 55, so 60 will come on the right side of our root node 55. Now we will check the levels. All the nodes are at the same level. Now only one node remaining. Now the last element that is to be inserted is 75. For inserting 75, we will again compare it with the root node. Root node is 55, so 75 is greater than 55, we will move towards 60. Compare 60 with 75. 75 is greater than 60, we will further move towards the right side of 60. Right side of 60 already contains 65, so we will compare 75 with 65. Since 75 is greater than 65, so we will insert 75 on the right side of node 65. So after inserting 75, the balance, the levels that at which these nodes are present will get again disturbed. That means on the left side we get a complete binary tree. On the left side of the root node we get a binary tree. That means 45 contains two subtrees, 25 and 50, and both are at the same level. And on the right side of root node we have 3 nodes, and those 3 nodes are not at the proper levels and not properly balanced. So here our critical node is 60. So for balancing this unbalanced tree, what we will do, we will again left shift our critical node 60 so that we can get a balanced tree. So after rotating or after left shift the critical node 60, we will get a node, a tree in which 65 will become our node and 60 will become its left child and 75 will become its right child. Now checking the levels, 55 is at level 0, 45 at level 1 and 65 at level 1, 25 at 2, 50 at 2, 60 at level 2 and 75 at level 2. Now all the nodes are at their proper places and all the nodes are fulfilling the proper conditions of binary tree. Proper conditions of binary tree means a binary tree should always contain the nodes which can have at most 2 subtrees. At most 2 subtrees means either no subtree or 1 subtree or 2 subtrees. So this is our constructed binary tree, and in this binary tree our root node has 2 children. Further moving, the left subtree also have 2 children and the right subtree also have 2 children, and all these non-terminal nodes, all these terminal nodes, that means 25, 50, 60 and 75 are at same level. So this is our final AVL tree, or we can say that a height balanced binary tree. So this is our finally constructed height balanced binary tree or AVL tree. So in this way we can balance the height of a binary tree, and this technique of balancing the height of a binary tree is known as AVL tree. So this was our topic about the AVL tree. I hope you all have understood. Thank you so much.